This is your first video for chapter 15. We're going to start with common ions, which are exactly what they sound like. They are ions that two things have in common. So notice this first example, we have a weak acid, we have HF, and we're adding some sodium fluoride to it. And sodium fluoride, because it's bonded to an alkaline metal, is going to dissolve. So really what you have is F-. And so you can see that F- is also in the acid equation or the reaction. So as the acid dissociates into H+ and F-, you're going to end up with some F- in the solution. So by adding some more F- from the sodium fluoride, it's based on Le Chatelier's principle, you're increasing the concentration of F-, and so it's going to shift to the left. As it shifts to the left, you're going to have fewer H+ ions because they're joining together to make HF. And as you have less H+, it means it's less acidic, and less acidic means a higher pH. So by adding a common ion, you can figure out which way it's shifting, and you can figure out what's going on with the pH. Let's do another one. This one down here, we have ammonium hydroxide, and we're adding ammonium chloride. So notice that they both have NH4+ in common. You can write out the reaction for the weak base of ammonia added to water, and you can see that you've got some NH4+ right here. So as you add that, again, it's going to shift away from that, which is going to decrease the amount of hydroxide. Hydroxide is what makes something basic, and so making it less basic is going to decrease the pH. And we're actually going to do an example. All right, so here's our first example. It says calculate the concentration of H+ and the percent dissociation of HF in a solution containing both some HF and the NaF. So notice that we've got this common ion of the fluorine. The first thing you always want to do with any of these equilibrium problems is to list out your major things. Your major species is what they're called. So let's see what we have. We've got some HF, and I'm not going to break that apart because it's weak. So weak things are mostly going to stick together. The only ones that you separate are going to be strong acids or soluble salts. We also have NaF, which is a soluble salt. So really what it has is Na+ and F- because those are going to dissolve. And then we also have some water, and that's about it. So now let's look and see which of these things are going to be involved in a reaction. The two things that are going to affect the H+ are the F- and the HF. These are the things that are going to control how much H+ that we have. The sodium is not going to do anything because the only thing it can bond to is the fluorine, and that would make a soluble salt, which would just dissolve, so it's not going to do anything. And the water, compared to the Ka value for HF, the water is going to be insignificant. So now we're ready to set up an icebox, and the way we know to set up an icebox is because we have a weak acid, so we don't know how much that HF is dissolving. That's what we're trying to figure out. Remember, you do not set this up for strong things, only for weak. And we can go ahead and add our initial concentrations of HF and fluorine. We don't have any H+, we have a little bit from water, so we'll put a little tilde, but it's close enough to 0 that we can say 0. We're going to shift towards the 0, and we have 1-to-1 ratios. We can set up our K equation. And we can plug everything in. And we can go ahead and make the assumption, so let's cross off these x's that we're adding and subtracting, which means x is equal to 7.2 times 10 to the -4th. You should always check it, but the assumption is good. And so now we know that x equals this number, and notice that x is also the same as the concentration of H+ at equilibrium. So we just stick a little unit on there for molarity, and now we know the concentration of H+. And then the last thing is the percent dissociation. We're going to put what we got for x over the initial concentration times 100. And that gives us our percent dissociation. All right, our next section is going to talk about buffers. So first you need to understand what a buffer is. A buffer is something that resists change in pH when you add hydroxide or protons, which is H+. So most of the time when you add one of those two, it's going to either make it basic by adding hydroxide or acidic by adding H+. A buffer is a solution that will keep the pH relatively the same even when you're adding those. And the way that it works is that you have two different things, and each of those things can react with either the hydroxide or the H+. And so as you add those to the solution, they're going to react and they don't actually build up into the solution. So there's two choices for a buffer. You need something weak and then its conjugate or its salt. So you can have a weak acid and its salt, or you can have a weak base and its salt. So here's what I mean. Here's the HF. Its conjugate is just F-, and notice that it's right here. So buffer involves something weak and its conjugate. Same thing here. We have NH3, NH4+ is the conjugate. So if you have the sodium and the chlorine are not included here, they're not really that important because they're just going to be spectator ions. But notice that each of those has something that has an H on one side and then it lost an H on the other side. Those are the conjugates. And buffer solutions are basically just going to keep the pH about the same. So what it says here, this is not really a new type of problem, but I am going to show you a shortcut that you can use once we get to the next equation. This is a better explanation of how it works. So here's the buffer solution. Notice we have a weak acid in its conjugate. So we've taken off the hydrogen, the H+, and now we have its conjugate base. So what happens is that if you add hydroxide to a solution of HA and A-, the hydroxide is a base, and so it's going to react with the weak acid, and you can see that you're going to end up with A- in water. Well, neither one of those two affects the pH because they're not H+ or OH-, and so they're keeping the OH- from building up. So it's not allowed to accumulate. Instead, you're going to accumulate A-, which is not an acid or a base. I mean, it's a conjugate base, but it's not the same as the strong base of hydroxide. Same thing with H+. So if you add H+, it's going to react with A- and form this weak acid. And weak acids tend to stick together. So instead of the H+ building up in the solution, you're going to end up with a lot of HA. Now, some of that HA will dissociate to create some H+, but notice that note down there. If the concentrations of A- and HA are large compared with what you added to the H+, then the pH is still not going to change. So the way that buffers work, though, is that they're not perfect. They won't keep the pH from changing forever. They just keep the pH from changing as long as you have something to react with the hydroxide and the H+. But if you continue to add hydroxide and H+, and you don't continue to add buffer, then eventually the pH will change. All right, this next equation is going to be your best friend. So this is called the Henderson-Hasselbalch equation. Sometimes just call it HH because it's so long. Not Hasselhoff, not to be confused with the guy from Baywatch, but this is Henderson-Hasselbalch. This is used in a buffer system, and this is going to save you from setting up some of these ICE problems. It's just a short equation. You plug that stuff in and you calculate it, and it's way easier. But you have to recognize when you can use this. So again, you can only use this if you have a buffer system, if you've got a weak thing and its conjugate. And notice that everything I have circled in purple, these are all in your reference packet as well, so you don't even need to memorize them. And it's basically just that the pH is going to be equal to the pKa, and notice over here the pKa is just the negative log of the Ka, plus the log of the weak base over the weak acid. So just make sure you put the acid on the bottom. And like I said, once you get those concentrations and you get the Ka, you just plug it all in and it'll give you the pH. And it'll save you from having to set up an ICE problem. These are valid if X is really small, but like it says here from a practical standpoint, it almost always is true for a buffer solution. So for a buffer solution, you can go ahead and make that assumption. But it does have to be a buffer solution, so you can only use it if it's a buffer solution. Here's an example of a weak base with its conjugate acid. We didn't do this yet, we did the acid one. So if you have a weak base and its conjugate and you add more base, you add H+, it's going to react with the weak base. If you add hydroxide, it's going to react with the conjugate acid. So again, the whole point of a buffer is that you have two things. One of them will react with H plus and one will react with hydroxide. So no matter what you add to the solution, whether you're adding H plus or OH minus, the pH is not going to change. So here's just a summary of buffers. Again, they contain a weak acid and its conjugate or a weak base and its conjugate. And this is how it works, that when you add H plus or OH minus, they each have something they can react with so they don't build up into the solution. And the pH of the buffer solution is determined by the ratio of the concentrations of the weak acid and the weak base. And that's kind of describing the Henderson-Hasselbalch equation. I'm going to do these examples, it says staff would do these. I'm going to do these in the next video. Let's just go ahead and finish up the notes section for today. The last section for today is the buffer capacity, and that is basically how well the buffer will be able to maintain the pH before it actually starts to change. So these two things right here are super important, that the pH of a buffered solution is determined by the ratio of these two. I've seen these on lots of multiple choice questions on the AP exam. That's why these are highlighted. But the capacity of a buffer solution is determined by how much the concentration is, by the magnitude of the weak acid and base. So pH is by the ratio, the capacity is by the concentrations. This is also, I've seen tested before, is how to prepare a buffer and make the optimal buffering solution. This is the best kind of buffer is when the concentration of the weak acid is equal to the concentration of the conjugate base. Because what happens is when you put them on top of each other in the Henderson-Hasselbalch equation, you get 1. When you take the log of 1, you get 0. And so this is going to be close to the pH. So the best buffer system is when those two are equal to each other. And then this table is just showing you that as you add H plus or OH minus, it doesn't change the pH very much if you have a buffer solution. And I'm going to do some more buffer examples for the calculations in your next video.